Hello, my name is Bayu Sutanto. I'm from Department of Mechanical Engineering, Politeknik Negeri Semarang, Indonesia. Today, I will present our paper entitled of Numerical Approach of Titanium Dioxide and Carbon Nanotube Nanofluids Flowing in Circular, Rectangular, and Triangular Tubes. Nanofluids produced from the nano-sized particle that have dimension less than 100 nanometer. At small quantities can be suspended in base fluids such as water, ethylene glycol, and any other fluids. Nanoparticle which has higher thermal conductivity than water, like titanium dioxide and carbon nanotube, can improve the performance of heat transfer coefficients. Research in our laboratories show the experimental works of titanium dioxide nanofluid has the optimal value at 0.1 up to 0.3% volume of particle concentration. And the carbon nanotubes has also been considered as a promising nanofluids due to the attractive physicochemical properties such as high thermal conductivity and extended surface area. Nanofluid can be studied in the experimental and numerical approach. For the numerical study, the two-phase model has been extensively applied to describe the nanofluid flow characteristics. The mixture approach in the multi-phase Eulerian model was successfully used to study the titanium dioxide nanofluid under uniform heat flux in circular tubes. Moreover, research by ME96-2021 also successfully reported to approach the heat transfer and friction factor characteristic of carbon nanotube nanofluid at low concentrations. These figures show the schematic geometry of smooth tubes with circular, rectangular, and triangular channel as inner tube based on our previous experimental works. The tubes from the copper material had a path length of 414 mm, and the outer tube had the outer and inside diameter of 25.4 mm and 23.4 mm respectively. And the hydraulic diameter for the inner tube is constant, that is 5.26 mm with the same thickness, that is 0.37 mm. Hot water flows in outer tube at 50 degrees Celsius with velocity of 1.58 meter per second, and the nanofluids flow in the counter direction in the inner tube at 20 degrees Celsius with a Reynolds number of 4,000 up to 8,000. The exit of tube is connected to the outer pressure that has the pressure of 1 atmosphere. The properties of nanofluid can be examined for the density and constant specific heat by using the mixing theory by using this equation, and the viscosity can be evaluated based on previous established experimental data. This is the property of titanium dioxide, carbon nanotube, and also the water. It shows that the conductivity of titanium dioxide is higher than the water, and the carbon nanotube is much higher than titanium dioxide and also the water. And in this study, the constant particle loading, that is 0.3% of titanium dioxide and carbon nanotube, were applied based on experimental analysis in our reference. The conforming equation consists of the continuity, momentum, and energy were used for multi-phase flow. The simplification, we use some assumptions like the steady state, incompressible, neglect the business screw approximation, and also the mixture model assumptions. The turbulent model of the K epsilon Reynolds group was applied to solve the conforming equation, with the convergence criterion is 10 power minus 3 for the continuity, x velocity, y velocity, z velocity, K epsilon, and the place 2. For the energy, the convergence criterion is 10 power minus 6. The multi-zone and hexagon mesh configuration were adapted to create this discretize the numerical domains. The mass independent study by varying the number of elements in the solid and fluid domain was carried out to verify the numerical results. It resulted that after 2 million elements in the simulation had error less than 0.15%, so it can be accepted for the mass independent study. The Nusselt number of the nanofluid is calculated by using this equation, and also we compare with the established equation from the Ditus-Bolzer and also the Petukov. And also the experimental approach from Christian et al. For the titanium dioxide nanofluid also submitted in this paper. It results that the titanium dioxide of the water nanofluids, this one, had a higher Nusselt number, about 10%, than the empirical correlation from the Christian one. It showed that the increasing of the Reynolds number also increasing the Nusselt number, and the heat transfer performance of carbon nanotube was higher than the titanium dioxide because it has the much higher thermal conductivity compared between the carbon nanotube and also titanium dioxide. This slides show the temperature contour for the titanium dioxide along the axis line and the cross section at x at 0.5 lengths for the titanium dioxide, and this one for the carbon nanotube. It shows that the velocity and hydraulic diameter remains the same for all Reynolds number. So the circular tube will have lowest mass flow rate because it has low cross-sectional area compared with the rectangular and triangular. So as the consequence, it has the highest mean temperature. And as the other consequence, it will produce the highest Nusselt number. The increase in the heat transfer due to the extended area does not necessarily increase the Nusselt number significantly. Although performance in the liquid phase condition, the present results are consistent with our previous works that the geometry has more substantial effects on the thermal performance because of its physical mechanism. And then the friction factor can be calculated by using these equations, and we compared with the established equation from the Bayu and Petukov equation. It shows that the increasing of Reynolds number will decrease the friction factor, and the nanofluid has the higher friction factor compared with the Bayu and Petukov because this is generally used for the water. And the conclusion is the number one, the titanium dioxide and carbon nanotube increase the heat transfer performance and Nusselt number with water-based fluid due to the higher thermal conductivity. The Nusselt number of the nanofluid increase while the friction factor decrease with the increment of Reynolds number. And the last one, the nanofluid flowing in the circular tube had the highest Nusselt number because its geometry has the lowest cross-sectional area compared with rectangular and triangular tubes for the same hydraulic diameter. This research was supported by the Institute of Research and Community Service Universitas 11 Maret Indonesia, and this is the end of the presentation. Thanks for your attention.